Okay, so in the previous lecture, we were discussing about improving the visual. What are the ways to improve the visual quality of image? Okay, so histogram manipulation technique we discussed, where we see that how the limited range of DN numbers can be extended to the available range of digital numbers. What does this mean? Let's say if in a given image, we have image of size n m cross n. Okay, so in the given m cross n image, it's, let's say if we consider it is 8-bit image. So when you draw the histogram, so in the histogram you can see that what is the range of digital numbers, okay, which are used to represent different ground resolution cells in the m cross n image. Okay, so in the histogram, on the y-axis we have a frequency distributions, while on the x-axis we have a, if it is 8-bit, so 8-bit we have a range from 0 to 255. Okay, so it will start from 0 to 255. And further we have a discrete numbers, one and from 1 to 255. Okay, and they are marked over here. So while plotting the histogram, you have already performed in the laboratory experiments. So what software does? Let's say it from 0 to 255. First, the input will be what is, how many bits are used for that particular image. So if this information is there, so we have a total range from, we have a range of digital numbers from 0 to 255. So the software will start for searching from 0. Okay. So let's say first DN number is selected 0, and all the elements in n cross m image is searched to see how many times 0 is present in the image. Okay. Let's say if it is present n0 time, so it is plotted over here. This distribution will be here n0. Similarly for 1, let's say it is n1. Similarly, let's say for digital number 2, the number n2. Similarly for till 255. But you notice that in most of the images, what happens, the entire display range, our entire range of DN numbers are not fully utilized. So in that case, what we do, all the elements in the given image is searched to see that what is the minimum digital number present in the image, as well as what is the max number of, what is the maximum DN number that is there. Okay. So if let's say the digital number, if it is represented by DNIJ, okay, so program needs to search first what is the mean, what is the mean, then further the program need to search what is the max. Okay. Now once we get information of mean and max of digital number, then we see the clear picture, like how many DN numbers are unutilized. So the unutilized DN numbers will be, once you plot it, it will be 0 to DN mean. Okay. And further from DN max to, let's say I write it 2 to the power n minus 1. Okay. If we have n is equal to 8, n bit, so it is 255. But generally we write it in a generalized form. Okay. So program calculate the range that is unutilized. So because why, what is the difference that is created? Like, let's say if our histogram is concentrated in a very narrow range. So what happens like once we see such kind of image? So why that contrast is not better? Visually that image is not like interpretable, we can say. So just see to plot this case on a over here. So let's say somewhere here we have a DN mean. It is coming here. Okay. And somewhere we have a DN max. Okay. And it's not a continuous function. It's a discrete. We have a different values for frequency. Okay. And once you interpolate it, you will get this kind of curve. So So once you connect these points, these are the frequency values corresponding to the distal numbers. So once you interpolate it, you will get a frequency distribution function PDF over here. Okay. So what happens if, yeah, in the given image, only this range is utilized. In this case, what is happening? Like once you see the image, and let's say we consider the two successive distal numbers in terms of their proximity. Let's say this is DN11 and this is DN12. This is the original image. Okay. From the original image, we are getting this histogram. Okay. And this is in very narrow range. 0 to DN mean and 0 to DN max to 2 to the power n minus 1. 8-bit, it's 255. These values are unutilized. Okay. Ultimately, see when we say that the on the basis of contrast in the image, visual quality is better. We can see in the image, in the context of the image, if the visual quality is better, it means we can able to difference the nearby features. Okay. So in order to difference the nearby features, so obviously there should be a difference in the intensity of color that is assigned, that is used to paint, let's say this these two particular cell. Differences can be seen if they are painted with a different intensity level of the color. Okay. It means by using this linear function we have discussed previously, like in this case we have a distal number, and in this case we have a different set of grayscale, and we have a transfer function. Generally we select it linear in nature. So you select a DN number, and corresponding to that you select what is a set of gray that you need to use to paint that grid cell. So if there is a differences to visually distinguish two nearby grid cell when you see it on the screen in the in an image form. Okay, so differences can be seen if there is a difference in intensity of gray color. If you are so it means, let's say there should be a difference. You need to highlight this difference to make the image visual quality better. I'm talking about in terms of single band image, and that is displayed using different sets of gray color. Okay, so to increase the visual quality of image or to distinguish the various features present in the image, what you need to do, you need to enhance, you need to increase the differences instead of gray. Okay, so gray intensity level needs to be highlighted, needs to be increased. So if you want to increase this over here, so similarly it can be done by increasing the difference in the digital number. Okay, so if this is your objective, how it can be done? Okay, so increase the contrast of the image. This is the process through which we can do it. Okay, so let's say when again I consider the earlier discussion over here. So ultimately the difference delta over here, that is D12, let's say minus, and DN11. This difference needs to be increased. Okay, how it can be done? Can we do it by modifying the existing by modifying the original image? And if we can do it modifying the original image, how it can be done? So what we do over here, by applying mathematical equation, we stretch this. Okay, so if you stretch this, and by stretching it, we can use various transfer function. So various kind of transfer function can be used to stretch this image, to stretch the histogram that is limited in terms of its DN range. Okay, so that the unutilized digital numbers are also can also be taken into the consideration over here. So we have a luxury to use these unutilized DN bands. So we can stretch it. In that case, DN mean comes to 0 and DN max goes to 255. Okay, without changing the frequency distribution. Frequency distribution will not be changed. Why it is so? Because it is one-to-one mapping, like one DN number you are modifying by passing it through a mathematical equation, and you generate a modified value. What does this mean? Like DN output that we are generating using the function of DN input, then DN minimum and DN maximum. Okay, and one linear equation we have already derived in the previous class.
Sir, is it mathematical expression for stretching?
Yeah. You attended previous class, no?
Yes, sir, attended, but not completed. Actually, sir, my in my side there was exam. That is why jammer was there. That is, and therefore I could not attend the whole class. Half I was attending, but half was left.
Okay, fine. Quickly, I will cover that part over here.
Okay, thank you, sir. Thank you very much.
You're welcome. So to generate DN output, now see what is the difference in the range of DN input and DN output over here. By process through the function, we are stretching DN input to generate output values. Okay. And the range of DN input is from, we can write over here, DN input, it is DN mean less than or equal to DN input, less than or equal to DN max. Fine. By process through a function that can be linear or non-linear, both cases. You can write it. This function can be, first case, linear. Linear part we discussed in the previous class. And second one is non-linear. We'll see it. The both cases, linear and non-linear, mathematical expression that is used to modify the value of input DN. Now, after process through this function f, DN output, now it is utilizing the entire range from 0 less than or equal to DN output and less than or equal to 255. Keeping in mind this process enhance this delta. Fine. So this I'm giving you 5 minutes time to kindly go through the linear function that we derived. Okay. I expect you to just see the equations. Okay. How this f linear I derived in the previous class. Then after 5 minutes, I will again discuss that with you. Like I would like to just see like how. Okay. Okay, so who will tell me what is the equation we have in case of linear histogram manipulation? In terms of DN input, mean digital number, max digital number, and DN output. So DN output in case of linear contrast manipulation, so it is if we have a DN input, DN mean, and DN max. So tell me the equation. What is equation for F over here? Rahul Kumar, could you please unmute?
Yes, sir.
Rahul,
Yes, sir.
what is the equation we derived in the previous class?
So dn minus d minimum upon d max minus minimum into 255, sir.
So let me just so. Wait. So DN output is equal to what I should write here? DN output is equal to
सर स्क्रीन नहीं दिख रही सर आपकी, शायद शेयर नहीं किया.
screen is already shared. Okay, please wait. Please wait.
Okay.
I hope now you can see the screen.
Yes, sir.
So DN output is equal to
Sir dn minus dn minimum and sir maximum minus minimum into 255.
DN input minus
Sir minimum dn minimum.
divided by
Sir dn maximum minus ds minimum.
minus DN
Minimum into
multiply
255.
multiplied by 2.
Yes, sir.
Okay, good. So by this transformation, okay, of a DN input to DN output, we'll see how we can enhance this delta. That is our requirement to increase the visual quality of image for contrast enhancement. Okay. Graphically, we can see that how it happens. So through the graphical analysis, the same equation can be plotted over here. And on the independent axis, we have a DN input. Okay. And on the dependent axis, we have a DN output. Fine. And we have a range. It's a DN mean to DN max. Okay. And all the pixels, all the DN numbers are in the input image. This original input image, all DN numbers are lying between DN mean to DN max. By using this equation, we are going to transform DN mean. We are going to stretch DN mean to 0 and DN max to 255. So just see how mapping is done. This is output axis and this is input axis. So DN mean is stretched to this location. Okay. Means one coordinate we have over here, and if it is stretched to this, So this will be the, and if we stretch it over here, okay. So here input is 0, output is 0. Here output is 255. So one line comes over here. This point will come over here. So we have 255 and 0. And this is the linear, this equation is linear in nature. So this will be the transfer function. Okay. What is the slope? You see that slope of this line is more than 45 degrees. Why it is so? If you draw a line, so if there is no intercept, y is equal to x, this is not like that. Okay. So the slope is more than 45 degrees. Let's say if you select two DN number, DN11 and DN12. At this location, we have a DN11. At this location, we have a DN12. Difference is already calculated in the input image. It is delta. Okay. So this is the delta over here. Okay. Now we'll see what is the difference corresponding to modified DN1 and DN12. So we have a modified DN11 over it is dash, and second one, this is modified DN12 dash. Now we'll see this difference is how it is propagated in the output image. So we have a difference over here, that is delta dash. Okay. So delta dash comes over here. Delta will be delta dash when slope is, when it will be, when tan theta will be 1. Yeah, this angle is 45 degrees. Delta dash is more than delta when the theta, if this is angle is theta, if this theta is greater than 45 degrees. And this theta is will be greater than 45 degrees. Why it is so? Sorry, this value will be extended over here. This is the location of DN max. Okay. At DN max, it is 255. This is the location of DN max, and somewhere here we have a 255 in the input image. Okay. So the shorter range, this range is DN max. If you while drawing this line, this entire range is less than this one. This is entire 255. This range is, while this range is less than 255. Okay. So this is reason why this theta is more than 45 degrees. And in that case, the differences between two distal number, okay, they are enhanced over here. Just see after the after applying this transfer function. Okay, so I hope you have understood the concept, how by changing, modifying the digital numbers, we can increase the differences in the different sets of gray color in terms of their intensity. So ultimately, visually, we want to enhance the image quality. Okay, it can be done, as I discussed before, by changing the intensity of gray color. Okay, by enhancing the intensity of gray color. Gray color intensity can, if you want to see the enhanced uh, intensity, enhanced difference in the intensity of two gray sets. So in the background, in the image, what you need to do, you need to increase this delta. Okay, this delta can be increased by enhancing the differences between two uh, consecutive pixels. Okay, and this delta can be enhanced in this way, as you see over here. So the range, the digital number range in the input image can be stretched to occupy the entire range from 0 to 55, and that occupancy could be in the linear format. Like this is the linear transfer function. So one part, linearity part, we have covered. Now we'll see how it can be non-linear and what is the effect of non-linearity in the visual quality of image. How it will affect.
सर सर
Mhm.
सर ग्राफ में जो आपने ये वाला पोर्शन बताया है, डेल्टा डैश इज ग्रेटर देन डेल्टा, सर वो
Mhm.
थीटा इज लेस देन 45 के लिए होगा ना? हाँ हाँ,
Say it
डेल्टा
again.
डैश नहीं नहीं, ओके सर, सॉरी, थैंक यू, हो गया सर।
Mhm. Okay, good. Okay, so second case, we'll see the non-linearity. DN input. For 8-bit image, we have an option to utilize entire range 255, but it is not a case. Some part of DN range is not fully not utilized, so we have a DN mean to DN max. Instead of writing MIN, just I'm writing small m, and MAX, I'm replacing it by capital M. What we should do, like one point is this, and second, the its output we have 255 again. Okay. If you see over here, DN max, it is this point is over here. So DN max to 255, and in the previous case, the linear transfer function is used, but it can be non-linear, like it could be like this. Let me use different color to plot it. Okay, so in that case, the DN output that is equal to.
Sir, on y-axis, there is frequency.
No, y-axis, I'm plotting this equation. We are not talking frequency over here. Okay.
Okay.
We are talking about how an individual digital number can be modified. It's not a histogram.
Okay, sir.
Okay. It's a
Yes, sir.
graphical representation of this mathematical equation. This one, where input we have a DNI. It's a x-axis. You can assume it's x value. For DN output, it's y value, and they are related with a certain mathematical function, that is f. If f is linear, then it will be a straight line. So when you plot it uh, using a graph over here, then this is a x-axis, independent axis. Dependent axis y will come. So in place of y, we have a dn output. In place of x, we have a dn input. And now we are seeing that how input digital dn input is modified such that this range can be extended to complete range 0 to 255. Same we do over here. If you see that, if we use this equation, see what we are doing. dn input, for dn input, we are assigned dn output 0. For dn, dn minimum, we are assigned 0. For dn max, we are assigning 255. Okay. And in between, the digital numbers which are there, they are further assigned a dn output using this equation, using this transfer function. Okay. Now the change in this case, also, if we use this exponential transfer function. Okay. So in this case also, what you are doing, dn min is assigned to 0 and dn max, that is dn max. The dn max is assigned to 255. Like just see. dn max, if you see this, but this is the dn max. Corresponding to dn max, we have a 255. But in between dn min and dn max, the digital numbers which are present in the input image, how they are modified. Are they modified linearly, or we are going to modify them non-linearly? So if these, like the first case, if you see, if I say this is F1 and this is F2, so this both F1 and F2 are non-linear in nature. I hope it is clear. If you see over here, this F1 is exponential, while what will be the nature of F2? Who will tell me? F2 will be, how you plot y is equal to log x. Try to recall the
Sir, asymptotic to the negative y-axis and going forward in concave downward direction in positive y-axis.
okay, like the F1 is exponential, and I talk about F2. What will be the nature of F2? Would you
Sir,
relate it with a certain
log
equation?
It's a log function only.
It will be logarithmic. It will be a log function. Fine.
Yes, sir.
Now we'll see by using exponential function and logarithmic function, ultimately how the quality of image is affected. Obviously, it is going to improve. But what portion of image will be improved? Where's the light part? Well, it is a dark part that we see over here. In the context of how this function is enhancing delta. Delta is the main parameter, this part. Okay. So what conclusion we have on the basis of this analysis using the linear function? To improve the visual quality of image by enhancing the differences in gray shade corresponding to 2 pixel like DN1. For simplicity, I have considered a generic example so that it will be clear with you also. DN1 and 2 pixel I have already selected. Okay. And on the basis of how we can distinguish the 2 pixels, so we have discussed that the difference in gray shade between these two should be increased. Obviously, if there is a color change, we can notice it. Okay, there are some difference. If there is not a major change in color, so we can't very clearly see. So we want to increase the change in gray color when we move from one pixel to another pixel, in this case DN1, DN. To do this, what we need to do, this difference we need to increase between these 2 pixels, the delta. And delta, we have seen that delta increase when the slope, if I say the slope of function, transfer function, let's say this is f, slope of transfer function f is more than 45°. Is this correct? This conclusion we have. And we have you have already clearly you have seen over here. If m is greater than 45°, then in that case delta dash is more than delta. And we enhance this delta difference by keeping slope of transfer function more than 45°. Okay, the same concept we apply over here, and we see that like what part of image is enhanced while what part of image is not enhanced. Okay. So one by one, we select the functions. In this case, if f is linear, the entire image is uniformly enhanced. F is linear, theta is constant. Okay, theta is constant for the given theta, and theta is constant as well as theta is greater than 45°. So in that case, the transformation of difference delta to delta dash, it is constant. Delta dash is constant. So we can say that image is enhanced linearly. It is linearly enhanced uniformly throughout the image. It's not like the darker part image is become more darker, lighter part of image becomes more lighter. But if there is variation in theta, in the non-linear function, theta varies. Theta is not constant. Slope is not constant. Okay. So in that case, what will happen? Like if we use an exponential function, just see over here. Okay. So if you solve the exponential function, at certain point, if you draw a tangent, this is the point where theta becomes 45 degree. Okay. And if we consider this section, we divide it into two parts. For the given exponential function, which range, for what dn input range, theta is more than 45, and what dn input range, theta is less than 45. So this is second part. In this case, just see, theta is less than 45 degree. While for this part, theta is greater than 45 degree. What is the conclusion? I think based on the previous analysis, like how this transformation affect the quality of image, and by looking at this change where we have a transition at theta 45, if we move, this is somewhere transition occurs. This is the some dn number. We can write it dn 45. Okay. All the dn which are more than dn 45, for them theta is greater than 45 degree, while in the previous case theta is less than 45 degree. So can you suggest the changes which will occur in the image when that image will be transformed by using this exponential function? In this case, lighter part of image will be enhanced. The conclusion is, if you consider over here, if lighter part of image, obviously for that case, dn number is high. Okay. If we consider dn input greater than dn 45, we'll say this is a lighter part of image because we have a large dn values. So for them, obviously you will assign the lighter shade of gray color towards white. For dn input less than for dn 45, this range, this we consider the darker side of the image. So by using exponential function, lighter part of image will be enhanced. The reverse will occur when we use logarithmic function. Just see. In this case, somewhere in middle transition occur. Let's say we select this. This entire range, I'm talking about this part. What will happen? Theta is less than 45, while for this range, theta is more than 45. So in this case, using logarithmic function, we can say that the darker part of image is enhanced. Because what happened? If we consider this case, so here theta dash is more than theta, while in this case, theta dash is less than theta. Is it clear to all?
सर ये फंक्शन 2 के लिए एक बार फिर से बता दीजिए.
Tell me what you are not understanding function 2.
सर
F2 क्या है?
F2 जो लॉगरिथमिक है फंक्शन,
ओके,
अपर साइड वाला, उसमें सर जो आपने ये कंक्लूजन निकाला, लाइक डेल्टा डैश इज लेस देन डेल्टा,
this is
क्योंकि
for
सर
delta dash delta dash is less than delta, this is can just see the arrow mark. This is for the exponential function.
Exponential function, yes sir.
Mhm.
And on that basis मतलब सर अभी इसके लिए लॉगरिथमिक के लिए अभी नहीं किया है क्या आप?
नहीं, जिससे ये नहीं, अब I would like to just understand from where I need to start. ये बताओ तुम्हें क्या चीज नहीं समझ में आई है?
सर मुझे ये समझ में नहीं आया कि जो अभी आपने लॉगरिथमिक फंक्शन के लिए बताया कि थीटा मतलब स्लोप्स जो है वो जो मतलब जो आपने क्रॉस मार्क किया है यहाँ पे
ओके
एक, उसके ऊपर वाले पोर्शन में जो हमारा थीटा आएगा वो लेस देन 45 होगा और उसके नीचे के साइड्स जो है वो थीटा ग्रेटर देन 45 होगा।
करेक्ट।
तो उसको हमने सर डार्कर और लाइटर में कैसे डिवाइड किया वो पूछना था मुझे।
ओके, सी करेक्ट। Lighter part of image means the shade of gray is towards white. Lighter part का meaning ये है कि it looks like white. So the shades of gray which are towards white color, they are called as lighter part of image. And and higher distal numbers are given to lighter part of image. Okay. And if you can darker part, it means the dn is towards distal number is towards dn 0.
Okay.
dn 0 के close जो distal numbers हैं, they are called as and they are assigned darker shade of gray color.
Okay, thank you.
If you remember the color assignment, that graph I would like to plot over here, then it will be more clear to you how the sets of gray colors are assigned on the basis of distal numbers. Okay. So in the last stage of color formation, we discussed the assignment of color. 0 to 255, we have input image, and the y-axis we have a different sets of gray color. Okay.
Yes.
So highest we have a white. At 0 we have a black. And this color is linearly assigned. So once you see the color image, once you see an image, single band image on your computer screen, so what it does, when you click the option to open the image, after that the distal numbers are read, okay, and corresponding to the magnitude of distal numbers, color guns assigned different shade of gray. Like if it is selected 255, the white is assigned, it is selected 0, it is black is assigned, right? Now, now as per the nomenclature terminology, I'm using the gray darker side and lighter side. So if let's say if I divide it in two parts, this can be called as a brighter side, okay, and this can be called as darker side. Instead of lighter, you can better to use brighter side, bright image, okay. So
yes.
it would, so brighter means it's towards white, okay.
Yes.
And darker, it's towards black.
Black.
So it's brighter, lighter, whatever terminology you want to use, you can use it. And it indicate it's towards white side, white color, it's towards black color, it's a darker. Okay. Now this, when I have categorized it, what is the range? If you come over here, we are talking about this part. For this section, it's a lighter image. For
Yes,
this
sir.
section, it's a brighter image. So
Yes.
if you see, this is projected over here. So this range, high distal number values. This range represent a lighter side of image, while this range indicate darker side of image.
Yes.
Okay. Now I hope it is clear.
Yes, sir.
Good.
Thank you, sir.
You're welcome. So if you see this logarithmic function over here, then Just wait. What happens over here? Like if you plot a tangent, here we can say that this Tn output is equal to certain log of Dn input. Up plus some constant, it is shifted over here. So in this case, this is the transition point. See the transition point m is equal to 45 we select. M is equal to 45, image is not enhanced. Slope is greater than theta. We write it, so m is equal to 1 over here. If theta is more than 45 degree, then only image is enhanced. Theta is equal to 45, no enhancement. Theta is less than 45, it is further kind of like we can further decreasing the difference. The quality will be more poor in that case. So here we have a two range. So this is the part of this entire DN number. Okay. Just see for this case, this theta is just monotonically decreasing. Okay. So entire range, theta is less than 45 degree. And once it tends towards the DN max, further it keeps on decreasing. Okay. We can say that lighter part of image is it's kind of suppression. Okay, the differences in consecutive or successive 2 DN numbers, they keeps on decreasing. While in this case, theta is more than 45 degree, and even highest slope we have towards the darker side. So darker part of image is more enhanced. Okay, it is strongly enhanced. Let's say if in the given image we have a dark scene and bright scene. So by using a logarithmic function, we enhance the dark scene, yeah, dark areas more. If our aim is to just only enhance the dark area, we are not considering the bright part of image. So what we'll do, we'll go with the logarithmic function. If we want to uniformly enhance the entire image, irrespective of whether the brighter and darker part, so we go with a linear function. If we are interested to only highlight the darker part of image, this brighter part of image, okay, in that case we need to go with the exponential function. One more operator we have that we call a histogram manipulation. Sorry, this histogram equalization. So this is another function. We call it histogram equalization. Okay. Through which we can change DN input to DN output to occupy the entire image. So I'm giving this as an assignment. You need to go through the histogram equalization function, just read about it and submit it as an assignment. Okay. So these are the spatial enhancement techniques and this is the previous case. It's a point operator. Point operator means only one digital number, input DN number is considered. It passed through this equation and DN output is generated. We have other operators also where in addition with the input DN number, its surrounding pixels are also considered to generate DN output. We call them the local operator. Okay. So in the further slides, we'll discuss about local operators. Okay. And they are used to spatially enhance the image. Objective is to in the further sections, the objective is to understand like what is how spatial enhancement can be performed using the filters. Okay. And what are the different types of filters? So spatial enhancement is a procedure through which the image digital number is modified, okay, based on the pixels in its immediate vicinity. In the spatial enhancement, what we do, let's say if we want to identify this central pixel. So in addition with the central pixel, we also consider the surrounding pixels magnitude to modify its value. So pixels which are in immediate vicinity to the seed pixel or input pixel are also considered. We call it local enhancement, and the operator which we use, they are called as local operator. So we have the various filters to do this. Keeping in mind using that filtering, we want to enhance the visual quality of image. It is further used to correct and restore images affected by system malfunctioning. Let's say while the image acquisition, for a particular moment, CCD is corrupted. Okay. So corresponding to that grid cell for which the CCD was corrupted while the image acquisition. So the faulty digital numbers are assigned. Okay, and it is treated as a noise. So faulty CCD leads to the false assignment of digital number. Okay, and that the digital number is treated as a noise in the image that is corrected by image spatial enhancement. Further enhance the images for the visual interpretation. Okay, and we can also extract the various features which are present in the image by spatial enhancement. So like all image enhancement procedure, the overall objective is to create new image from the original image data, keeping in mind to increase that while the operation, by performing it, the overall information present in the image is increased. And that will further help us to better visual interpretation of the image. One more point I would like to add over here in the histogram manipulation. This process is reversible. You need to keep in mind. Like, see, the original image is modified. The digital number in the original image is modified to